Section 115 is on linear inequalities and compound inequalities. First, our objective, we're going to solve some linear equalities in one variable, numerically and graphically. Then we're going to use properties of inequalities to solve linear equalities algebraically. Then we're going to solve the compound inequalities algebraically and talk some more about interval notation and how we can represent inequalities in interval notation. Okay, so starting off here, I've got two equations. These are the life expectancies for men and for women born after 1980, modeled by this equation, and I want to complete this table. So I'm going to have this table autofill. I want this to autofill. So I'm going to go over to Desmos, into the grapher. I don't need the matrix calculator anymore. Enter my two functions. W of x equals 0.109x plus 77.5, and m of x equals 0.192x plus 70.0. And then we want a table, and we need values counting by fives for our inputs, all the way up to 40. And then for our outputs, we want to use the W function, input the x1 column, and then the M function, input the x1 column. So I'm just going to make this a little wider so I can see outputs for both of those. I'm going to pause while I write those down. So you can pause here if you want as well. And because it only had a tiny bit amount of space in each of those boxes, I rounded my values each to one decimal place because I just could not fit the numbers otherwise. For people born between 1980 and 2020, do men or women have greater life expectancy? So it is looking like the women values are always higher than the men values, so our answer is going to be women. And is the life expectancy of men or women increasing more rapidly? So if I look back at our equations, I can see the slopes, which are the rate of increase. The men's equation's value is higher than the women's, so the men's life expectancy is increasing more rapidly. So we expect them to intersect because the women's equation starts off lower, or starts off higher, I meant to say higher, but it grows slowly compared to the men's equation, which starts off lower, but grows a little more quickly. So they will eventually intersect. So we want to determine when the men's life expectancy is going to become greater than the women's life expectancy. So we're going to solve an inequality. Okay, and next page. Substitute the appropriate expressions in to write the inequality. All right, so the inequality that we want is when is m of x greater than w of x, and then we need to put the actual function for m of x here and the function for w of x here. So I need to look back at the men's equation real quick. That was 0.192x plus 70.0, and I want that greater now than the 0.109x plus 77.5. So the men's equation larger than the women's equation. Okay. So we're going to solve these numerically and graphically. So first of all, we want to solve it numerically. That is, make a table and continue to put in inputs until we can find out where the solution is. All right, so I already have my table started, but I can't see the solution yet, so we're going to just keep going. Okay, women is still higher. Women is still higher. Women is still higher. Yep, still higher. Okay. Women is still higher, but not by much. Ooh, barely, barely higher. Men, oh, still higher. Men hit higher. Okay, so I know that my answer is somewhere between 90 and 95. So I can try 91. Let's see. Oh, hey, the men's got higher right there. So when 90 years after 1980, the women's life expectancy was still just a little bit higher, but by 91 years after 1980, the men's life expectancy was higher. So we can estimate that the solution for x right here, that x is going to be, well, not equal to, but for any value that is greater than 91, right? Any x value greater than 91, the men's life expectancy is going to be higher. So it certainly is greater than the women's for 91 and for 95 and for any year after. So not just when are they equal, but when does the life expectancy for the men get larger than that of women's for any x value bigger than 91. Okay, so that's my estimate. We should interpret this result because it's a contextual example. So we want to say that this is 1980 plus 91. So men born after 2071 will have a life expectancy greater than women. And after just means anyone born in this year or after will have a life expectancy greater. All right, so are we certain about this? I would also just note about this that this is a pretty far extrapolation from the data. 2071 is quite far into the future. And we know that when we make our extrapolation predictions, they are less likely to be true than when we make interpolation predictions. So this is the best prediction we could currently make that far out, but we can't be very convinced of its reliability. So just a verbal note on that. Okay, now we're going to solve it graphically. Okay, so I'm going to, since I already have a table, it's easiest just to go ahead and use the table. So I'm going to zoom over on that table. I'm going to turn the dots off though, because the dots will make it harder to see where the intersection point is. If I click on it, that special point right there that I wanted to find for the intersection point, if all those dots are on the graph, it makes it harder to see where this dot is. Especially when you have dots very close to it. I want to make sure I can find the correct intersection point, that gray dot there. So I knew from the table that it was somewhere between 90 and 91. Now I can see that it's actually 90.3. So if I wanted a little more precision here, it's I can go into the 90.361 years after 1980. So I'm looking for that intersection point. It is 90.361, comma, and I actually know what their life expectancy is, 87.349. Okay, so this means that the x value is again greater than, this time I know it's 90.361. I have some more precision on my solution than I was able to get before from the numeric estimate. So the one we made before was really an estimate, rough guess estimate. We can get much more precision graphically and algebraically. All right, we can add to this description. So men born after, if I was going to interpret this value as a year, since it does not meet halfway between 2070 and 2071, I'm going to say 2070 in my description. Will have a greater life expectancy than women. But I get to add more detail now because I actually know that their life expectancy is going to be larger than 87.349 years. Could I have gotten that kind of information from the previous? I could have. I could have plugged 91 into either one of these two equations to figure out the life expectancy would have been. They should be similar. They won't be exactly the same since this value was not very precise, but I could have gone back and determined what life expectancy was from my guess. But I get it immediately from the ordered pair, so I wanted to just interpret both values here. Okay. Part A, graph. Part B, determine the intersection point, and what does it mean? We did all that, so I guess we're supposed to just graph it for part A, but we did all that already. Part C, solve the inequality graphically. Did that. What? To solve this, we need to determine the values. Oh, how does it compare? Got it. How does it compare to the solution from problem 3? So it's more precise. Okay. So it's more precise than our 91, right? It's more precise. We have 3 places. And we have the output. Right. Now, number 5, we get to do this. No, I thought we were going to do algebraically, but algebraically is down here. We're going to instead make a new inequality to determine the years when women's life expectancy is going to be at least 85. So just the women's equation this time. That was the 0.109x plus 77.5. And I want their life expectancy to be at least 85, so greater or equal to 85. So at least is going to include, could be 85, and it also could be higher. Solve the inequality numerically and graphically. Okay. So I'm going to get my Desmos graph open again. I'm going to keep this, just going to turn the men's equation off right here for a minute. Keep this women's equation up here. I'm going to keep this table, but I'm going to make a new table. Actually, I don't need a new table because I can actually see the women's table from this one. 85. Have we made it to 85? Oh, yeah. We made it to 85 here. And let's see if we can put in a couple more. Like if we had been at 69. Oh, we were still at 85. So 68. Not there yet. So it looks like we are going to be between 69 and 68 and 69 when women's life expectancy reached 85. So I would guess numerically 69 years after 1980. So numerically, my guess would be for x greater than 69. And again, it's from that table showing us that our output was 84.9 in 68 and 85.021 in 69 years after. So we would say that, again, we're 69 years after our starting year, which was 1980. So that puts us into the year 2049. So women born after 2049 will have a life expectancy of at least 85. Okay, let me get my decimals all the way out of the way there. Women born after 2049 will have a life expectancy of at least 85. All right, so use my graphing calculator to solve this inequality graphically. Okay, I don't have all the parts that I need yet. I have this side, the women's equation graphed. I do not yet have the 85 graphed. So to graph that side, again, as an output value, I would graph y equals 85. And then I can see the 85 output, and I can see where my function crosses it. And I can see my ordered pair here of 68.807, comma 85. So I'll get my Desmos graph out of the way. And a quick sketch, it was looking like this for that ordered pair solution. So we can be a little more precise in the actual x value. So we can say that this is for x values greater than 68.807. But when I put this into a sentence, it's actually still going to say the same thing because this would round up to the nearest year being 2048.8 or 2049. So we would still say that women born after 2049, we'll have a life expectancy of at least 85. Now, in this case, I knew the 85 in the first because it was already just a whole numbered value. I didn't have to wait until the graph to find the y-coordinate. I knew it from the original equation. Okay. Now, the next part on algebraic. We're going to look at operations that can be performed on inequalities. So we're going to start with the statement 15 is greater than 6 as an inequality. So 15 is greater than 6, which is true. We're going to now add 5 to both sides to the inequality. So if I add 5 to both sides, that would be 20 is greater than 11. So that's still true. All right, subtract 10 from both sides. So if I subtract 10 from both sides, again, of the original, that's going to be 5 greater than negative 4. Still true. So we're exploring what operations are okay. So it's okay to add to both sides, right? Add to both sides. It's okay to subtract to both sides. Those things have been fine so far because they're still true. Multiply both sides by 4. So 15 times 4 is 60. Greater than 6 times 4 is 24. That's still true. So we can multiply each side by 4. Now we're going to multiply each side by negative 2. So that's going to be negative 30 is greater than negative 12. And that is not true. So it is not true that when I multiply by a negative value, that I still have a true statement. So in order to have a true statement, if I multiply by a negative, we actually need to reverse the inequality because negative 30 is less than negative 12. So I can add or subtract things from both sides. I can multiply both sides by a positive and divide both sides by a positive. But when I multiply or divide both sides by a negative, if I don't switch the inequality, it is not true. We need it to be still true. So we have to reverse the inequality symbol to make it true. So again, this is a demonstration of some of the standard rules of inequalities. Okay, so in property 1, if the same quantity is added or subtracted to both sides, then or divided by or multiplied by a positive number, then the inequality is the same. Property 2, if you multiply or divide by a negative number, that's the important one, then you have to switch the inequality. So if you multiply or divide by a negative number, the inequality symbol must be reversed. Okay, a couple examples of that. We're going to go on to number 7. This one, I also want to note in this example that they show the graph on a number line of an inequality. And I'll mention that this is the inequality right here for x is less than 3. And there is an open circle right here to signify that this is not an inclusive inequality. If it had been inclusive, like x is less than or equal to 3, we would have had that same number line, but we would have had a filled in closed circle instead of an open circle. The open circle goes with the exclusive inequality, and the closed circle goes with the inclusive inequality. So with the equal bar closed, no equal bar open. Okay, so I want to solve this inequality. This is the life expectancy inequality algebraically. So the first thing to do would be to move the x's to the same side. To above this, I'm just going to subtract off the 0.109x from both sides so that I can move I forgot the 0 there, but I can move the x's from this side over to this side. So if we get our calculator here for the computation, I'm just going to make a new one real quick. I need to take 0.192x minus 0.109. I did not mean to type the x. I meant to say it, but not type it. So I should get here 0.083x plus 70 is greater than 77.7 or 77.5. Okay, now subtracting 70 from both sides, we're getting this x by itself. Negative 0.083x is greater than 7.5, and we're going to divide by the 0.083 both sides. So x is greater than, I don't change the inequality here because we did not divide by a negative. I need to take 7.5 divided by 0.083, and I get 90.361, etc. for x. All right, I want to compare this with what we did when we did this graphically. So if you look back over here, when we did this one graphically, we also got 90.361 for our x value. So that's the men's life expectancy is going to be larger than women's life expectancy for men born 90.361 years after 1980 or born after 2070. 2070. I think I said I was going to write 2070 on this one. Didn't. Meant to. 2070. Because it's not going to round up to 2071 like this one had with a 91. So, all right. Moving on to number 8 here. We're in a fitness club. We're doing some exercise, and we have some target heart rate information. We want our, depending on our age, we want our pulse rate to be larger. This is our lower boundary than this expression, and lower, this is our upper boundary than this expression. So determine my lower value and my upper value. Oh man. So if I figure this out, I have to pick and say what my age is. So not gonna do that, but I'm gonna pretend to be, how about 35? I'll say if A is gonna be 35, what does that do? So you can do something different for these A values. It's just based on some A value that you choose, plug it in, and determine the lower and upper value for this human, this 35-year-old human that we're imagining here. Okay, so lower boundary, 0.7 times 220 minus the A, which is going to be 35 here. So we have 129.5, and then the upper boundary is 0.87 times 220 minus the age, which again we'll pretend is 35, and so that would give us 160.95. Okay. Oh, I made a mistake in the lower. I forgot the 2 on the 7 somehow. So that's actually 133.2. Okay. Sorry about that. 133.2. I think everything else looks good. So let's see what we can do next here. Okay. So that would be our A values. And it says for, if I had chosen 20, I guess maybe I should have read below and picked 20, but they wanted me to pick whatever my A value was to start with. We wanted the pulse rate to be between our lower and our upper of 144 and 174. And graph, this would be all numbers between 144 and 174, open circles on those because the inequalities are non-inclusive, and then connecting between them. Okay. I don't get to do anything with that yet. We'll get to do something with it in number 10, it looks like. So first, we're looking at life expectancies again. So it says this one is the life expectancy formula for men. I want to write a compound inequality that can be used to determine in what years the men's life expectancy will be into their 80s. Okay. So into their 80s. So the lower boundary for being in your 80s is when you hit 80. And when you hit 80, you're in your 80s. So that's going to be the lower boundary, and it's going to be inclusive because when you hit 80, you're in your 80s. And our men's equation is going to be larger than that. It's going to be between that and, now I'm not going to, oh man, gotta think before I draw things here. I'm not going to put 89 right here because they're still going to be 89. They're still going to be in their 80s when they're 89 and a half or 89 and 3/4. They're still going to be in their 80s until they hit their 90th birthday. So I'm going to put a 90 here, but I have to make sure that I don't put the equal bar on this side because when I am 90, I'm not in my 80s anymore. But that last day before my birthday, when I'm 89.9, I'm still in my 80s. I just have not yet hit 90 until the next day. So one of these is going to have the equal bar because when you're in 80, you're in your 80s, but when you're 90, you're not. And so this is a compound inequality with mixed symbols. So we could have inclusive and exclusive in either order, exclusive, inclusive, or they can both be exclusive or both be inclusive. I guess in case we couldn't figure that out, they wrote us the equation from number 9. We're going to solve this algebraically. So 80 less than or equal to 0.192x plus 70 less than 90. All right, when I solve this, I need to get x by itself. And since the x is in the center, I'm going to work away from it. Whatever I do to the middle, I have to do to all 3 sides. This is an inequality with 3 sides. So if I subtract the 70, I have to subtract the 70 from all 3 sides. So I'll have 10 less than or equal to 0.192x less than 20. And then we're going to divide by the 0.192, again, all 3 sides. Okay, need some calculator help here. We are taking 10 divided by 0.192, and then we also need to do 20 divided by 0.192. So that gives us 52.08 less than or equal to x less than or equal to 104.17. Okay. So those are years after 1980. So if I take 1980 and we add 52.08, puts us in 2032. And if we take 1980 and we add the 104.17, that puts us in 2084. So I'm going to write over to the side over here, get rid of my decimals window for a second, that men born between, I got to get decimals back because I forgot. Men born between 2032 and 2084 will have a life expectancy in the 80s. Now, the English language isn't quite as good about determining inclusive versus exclusive inequalities. So I want to indicate men born between 2032, I'm going to say or in 2032, and then up to 2084, but not in 2084. So if they are born in 2084, they actually live into their 90s. So just between, strictly between for the 2084, but it could include the 2032. So we'll have to specify that in a few more words just to make sure that the inequality is inclusive on this side and exclusive on the other side. Exclusive on the other side. Trying to match it up and just got carried away. There we go. Okay. Now the interval notation part. Okay, so our our inequality that is exclusive, the one that has the no equal bar, is going to be matched with a parenthesis, and the one that has an equal bar is going to get matched with a bracket. So this one is open. An open interval does not include a value, and then a closed interval has the endpoint. So we're closed with a bracket if we include the endpoint. And they can be half open or half closed, depending on where the inequality symbol is. Okay, so there's a couple things here that are written in inequality notation. We're going to switch them into interval notation and vice versa down here. So I want to include that -5, so we're going to bracket around that -5 up to 10, and we're going to bracket that 10. We're going to bracket from 4 up to 8.5, but 8.5 is going to get a parenthesis because it's not included. We're greater than -2, so -2 is the smallest number, parenthesis not included. It goes up to infinity because it's just everything bigger. We are less than, so if we're less than, we're getting smaller than. So getting smaller than, it means that the 3.75 is the largest value. And if that's the largest value, then we should go all the way down forever down to -infinity. Okay, so vice versa, back into inequality notation. So -6 is my smallest value. X is between that and 4. I get to include the 4. It's got a bracket. This is going to go all the way down to -infinity. So this is going to be x's that are smaller than or equal to 1.5. X has to be between -2 and 2, both exclusive, no bars. And x has to be larger than -3, going all the way up to infinity, larger than -3, no bar, because there's a parenthesis on that -3, not a bracket.